Okay, 7.4 takes all of these arithmetic sequences and geometric sequences and talks about what their graphs are. Okay, so to begin, an arithmetic sequence, reminder, is a sequence of numbers in which the difference between any two consecutive terms is the same, right? Meaning you add the same amount each time, right? Now with that, when you graph it, right? When you graph a arithmetic sequence, it ends up being a line or linear, which means the graph will look like a straight line. Okay? Remember, the common difference is basically the amount being added or subtracted each time. And then in addition to that, right, the common difference ends up being the slope of the line. Okay? Now, common ratio is the constant ratio between any two consecutive numbers in a geometric sequence, right? It's the amount you're multiplying by each time. Okay, now when you have a geometric sequence, you get one of two things. You get exponential decay or exponential growth. Exponential decay is a quantity that starts real high and decreases quickly, where exponential growth, right, starts out low, and as you go to the right, or as x gets bigger, the y value grows. Okay, now exponential decay and growth, right, relates to a geometric sequence, right? Decay is when your rate is a proper fraction, right? And growth is when your rate is basically a whole number, right? Or a number greater than 1. So a geometric sequence is a sequence of numbers in which the ratio of any two successive terms is equal, right? And basically that means you're multiplying to get the next number, okay? All stuff we've talked about already. So when you're given this table, right, the directions say to determine if this is, so it says the growth of prize A is, right? When we look here, prize A, if I look at my y values, what's happening each time? Is it showing that it's an arithmetic or a geometric sequence? I can multiply 2 by 2 to get 4, but if I do 4 times 2, I don't get 6. So if I add 2 here, and I add 2 here, I add 2 here, right? Because I'm adding the same amount each time, that means it's basically linear growth. If it's arithmetic, it's linear. The y values increase by the same amount over each interval. The change in the y values is 2. The sequence is associated with this function is an arithmetic sequence, and the common difference in the sequence is 2. So if we had to write the first 10 terms of this sequence, we would start with 2, 4, 6, 8, 10, 12. The next one then would go up 2 to give me 14, 16, 18, and 20. So when we look at this table, if this is prize B, what is the growth of prize B? Well, if I look 2 to 4, 4 to 8, 8 to 16, what am I doing each time? I'm multiplying by 2. Right? So the growth of prize B is exponential. Okay? The y values are increasing by a constant factor over each interval. Each y value is 2 times the previous y value. The sequence associated with this function then would be a geometric sequence, and the common difference in the sequence is 2. It is 2, but this should be common ratio, right? And the sequence is 2. So if we had to write the first 10 terms here, the numbers are going to grow much quicker. 2, 4, 6, 8, or 2, 4, 8, 16, 32, 64, 128, 256, right? Then 512, and then 1,024. So if you were to win a prize, you definitely would want prize B. Okay? So when you look at the graph of A, notice if you have an arithmetic sequence, you have a line. If you have an exponential or geometric sequence, you have exponential growth or decay. So at the end of 6 days, prize A, right, when we look at prize A, what do we notice about it? Right, sorry, not prize A, but prize B has a greater payout. At the end of 1 month, prize B has a greater payout. Prize A continues to grow for 2 more months. At the end of 3 months, prize A's payout will be, right, what will it be? Will it be greater than or less than? It would be less than prize B's payout after 1 month. Okay, so the next one, a quantity, right, a quantity increasing exponentially will eventually, right, exceed a quantity that's increasing linearly, right? So no matter what, even if in an exponential function, even if the line starts out above, eventually the exponential function will catch up. So consider this table here. Is this exponential or linear, right? So if I look, what is happening here? Am I adding the same amount, subtracting the same amount, multiplying by the same amount, or dividing by the same amount? If I look, I'm dividing each one of these by 2. And dividing by 2 is the same as multiplying by a half. Since, right, we are dividing or multiplying, it's exponential, right? That's what makes it exponential. So what is the explicit formula for this? It would be a sub n equals, what did we start with? 72 times 1/2 to the n minus 1 power. Remember, this is your initial amount. This is your rate of growth. All right? If we had to use the explicit to find the value of the 6th term in the sequence, we would say a sub 6 equals 72 times 1/2 to the 6 minus 1. And when you evaluate that in the calculator, right, you would get, what does it end up being? You would get 2.25. All right. Next one, if this is your table, is it linear or exponential? What do I notice is happening here each time, right? Here it is going up 3 each time. Since it's going up 3 each time, it's arithmetic, which makes it linear, right? Since it has a common difference, right? It would be linear. So, what would the explicit for this be? Well, what's our initial amount here? Our a sub 1, right, our first term, is -7, and our basically common difference is 3. So we would say a sub n equals our first term plus our common difference times n minus 1. Okay, so that's basically reviewing everything we've done. So what would the value of the 6th term be in the sequence? Well, a sub 6 is equal to -7 times 3, plus 3 times 6 minus 1. Let me rewrite this. A sub 6 would be -7 plus 3 times 6 minus 1, which would give me -7 plus 3 times 5, which ends up being 8, because -7 plus 15 would be 8. All right. So, if we had to fill in the blanks here with increasing, decreasing, growth, decay, or graph the letter, right? when you look here, for linear functions, right, the slope is the common difference. When the x values are equal intervals, the y values form an arithmetic sequence. When the common difference is greater than 0, the linear function increases, right? An example graph is graph C here, right? So if I look at C, my common difference, right, is greater than 0, you know it's going to increase from left to right. When the common difference is less than 0, the linear function is decreasing, right? As in example or graph A, right? If I look, I'm going down each time here. For exponential functions, the y values form a geometric sequence, right, when the x values are in equal intervals. When the common ratio is greater than 1, it is exponential growth, right? As an example, if I look, exponential growth from left to right, which one grows, where the y values shoot up real quickly, that would be in graph D. Okay? And when the common ratio is greater than 0 and less than 1, it is exponential decay, meaning you're starting high and dropping, which would be graph B. I start high and it drops real quickly, right, in graph B. So let's look real quick at the checkup problems. All right, and looking at this, the function represented in the table is linear. How do we know? Well, we know it's linear because it has a common difference, right? It's linear because it has a common difference of 2. What would the fifth term be, right? If it's going up 2 each time, a sub 5 would be 109 plus the 2, which would be 111. Okay? Now the next one, the function in this table, right? What would this be? How do we know it's exponential? Because, do we see a common ratio here? Yeah. Each time I'm multiplying by 3 here. So I know it's exponential because it has a common ratio of 3. What would the fifth term in this be? Well, when I go ahead and multiply the fourth term by 189 times 3, a sub 5 would be 189 times 3, which would be 567. Okay? Now, is this function represented in the table linear or exponential? Why? Well, if I look here, am I multiplying or adding the same amount each time? If I look, I see I'm subtracting 5 each time. Subtraction is kind of a form of addition, so we would say this is going to be linear, and it's because it has a common difference that's equal to negative 5. What would the recursive rule for this be? Well, I know I'm going to state my first term, a sub 1 equals 14. Remember, now we have to talk about a sub n is, what are we doing to the previous term? We're taking the previous term, a sub n minus 1, and we're not adding, we are subtracting 5 each time. All right. Okay, so when I look at this table, is it linear or exponential? Well, if I look here, what's happening each time? It's tough to tell what's happening from 2/5 to 2, but from 2 to 10, I'm multiplying by 5. From 10 to 50, I'm multiplying by 5. Therefore, I know it's exponential because it has a common ratio of 5. what would the explicit rule be? It would be a sub n equals, right? I'm going to take my initial value, 2/5, and multiply it by 5 to the n minus 1. Remember, a sub n equals your initial amount, a sub 1, times your rate of growth, which is your common ratio, to the n minus 1. Okay? So, categorize this as linear increasing, linear decreasing, exponential growth, or exponential decay. Since it's a straight line, we know it's linear, right? And since you're going uphill from left to right, we know it's linear increasing. Alright? Since on the left hand for number 10, you're starting real high, right? And you're decreasing real quickly, right? What we say about this is we say this is exponential decay, meaning it's decreasing real quickly. Okay? So go ahead, try this.